a bit nervous. Okay, so you should be able to see a slide that says OSIS finding exponential cutoff in the size distribution of the Kuiper Belt. That's the wrong slide title. But let's see if I've got the right slide. Yes, I do. Great.
We can see it.
Thank you very much.
Yeah.
Yes, we're partway there.
You like this better.
This is way better. So, yeah, so this is I'm going to talk to you about, first of all, planet formation, which is really the motivation for what we're trying to do with the New Horizons mission. So New Horizons is a small spacecraft about the size of a small car, usually say Volkswagen Beetle. And the spacecraft is has an optical imager, an infrared imager, and spectrograph on it. And what we're trying to do is to measure details about the planets in the distant solar system, and from those details, put together an idea of how the building blocks of planet formation were put together. It's a real mystery still in planetary science. How do planets actually come into existence? So this is our solar system, just to kind of get a perspective where we're at. Right, we got the big giant planets, Jupiter and Saturn, the ice giant planets, and then the Earth and a few others there. And so it's a little bit it's quite an ensemble of things, right? And somehow there's a process that makes all of this material, and that's the kind of question of what's going on. Okay, so here's an artist's model, an artist's conception of a physical model. So what I'm going to show you is a little movie. I'll let the movie run actually here. Hopefully over Zoom you guys can see it okay. So this is a perception of how planetesimal formation or how planet formation happens. The big gas of dust surrounding some central star-like body, and as the clouds disperse, voila, you have planets that are forming by collisions of material in this disk as it wanders around and becomes harder and harder for collisions to happen, but eventually they build up into planets, and you have this disk of material that's planets orbiting around a central star. And that's planet formation. So that's an artist who's taken what is really our current model of this process and kind of put it together in this video sequence, right through to the planets going across stars and seeing there's the Earth. So that could be how this happens. And so that's one conceptualization. And then if I go to the next one here, here we go. Oh, I'll go to the next slide. So here's another visualization of a different process. So you have a bunch of gas going around a star, and we can see these streamers of material kind of forming around that star. And if we just wait for a few more times for the streamers to go around, little planets will start to pop out in the densest regions in those spirals of gas, and bang, there are planets, and that's how planets form. And that's a very different process, right? Those two things are completely different. They rely on different kinds of physics. One is heavily driven by gas and liquid fluid dynamics kind of calculations and trying to understand how fluids behave, and the other one's driven by just pieces of dust running into each other and sticking together. And they have very, very different processes. And we don't know which one's right. We can make both of those work in models. And we can make both of them not work in models, depending on how we set those models up and what parameters we use. So we'd like to understand which of those two models is probably correct. Make sure I go to the right computer. So, okay. So we have some hints. This is the moon, our nearest object of interest. And there have been missions to the moon, and rocks have been brought back. And so the rocks are brought back from this basin over here. You can bring those rocks back to the Earth, and you can measure how old they are using lead isotope ratios of radioactive decay. And you get that rock from that basin, they're about 3.83 billion years old. You can do another basin down here. You can get ones that are 3.85 billion years old. And you go over here, let me just make that smaller for myself, right? And you start to see a trend here amongst these basins. They're all about the same age. Here's one or two more. Okay, so the lunar surface is full of impact basins and those impact basins are 3.85-ish billion years old. That means that 3.85 billion years ago, there were large impacts into the surface of the moon. These are giant impact basins. These are caused by objects that are probably 50 kilometers across, impacting into the surface, tens of miles across. So really large impacts. Okay, now we can go on the Earth and we can, oh, and I was going to start off by mentioning, right, it's International Women's Day. And so I'm trying to highlight all the women who are doing research related to this material presented in this talk, who really were the drivers of a lot of their work. And this is Barb Cohen, and she works on the lunar surface, trying to understand the lunar surface, but not by going to the moon, by collecting rocks in Antarctica and finding out which one of them are lunar rocks. And we know that because we have some lunar rocks that we went to the moon and got, and these ones look just like those. We know these are actual lunar rocks that have landed on the Earth. They're on the Antarctic ice sheet, quite pristine. You pick them up, you bring them home. There's about 20,000 lunar meteorites in the US Geological Survey collection, and Barb is busy trying to understand them. So inside of those rocks that came from the moon and on other rocks that are in Antarctica, if you break open those rocks, you can find these little tiny crystals. They're the hardest thing. You think diamonds are hard. Zircon is much harder. And these zirconian crystals are preserved from the early formation of the Earth. And they are the only things we have from the very, very beginning of the Earth's formation. And they're about 4.4 billion years old. Okay, so the Earth formed, at least its structure of its surface formed 4.4 billion years ago. And we can find rocks that are from the moon that have in them zircon crystals that are from the Earth. Okay, so there's material from the Earth has been bound up into rocks on the lunar surface, which have then been returned back to the Earth through impacts, which is really weird to think about, right? So or something formed on the Earth, something hit the Earth, that material went off the Earth, got captured around orbits, hit the moon, gathered on the lunar surface, was bound up into a rock. And another object hit the moon and spit the rock that formed back to the Earth.
Oh, that was amazing.
That's really weird. Okay, so there's all kinds of exchange like that going on, and so we can get good clocks for what's going on in the planetary system. And you just saw that the basins were 3.8 billion years old, and these zircons are 4.4. So we have 600 or so billion years, or 600 million years of time between the formation, and there's still stuff moving around and impacting. And that looks a lot like that picture, that first picture, where there was a disk of material and stuff interacting. It's a slow process and stuff takes its time, and not that second picture where very quickly planets formed. And so a lot of people really like the slow process and try to figure out how to make models to make that slow process work. Oops, sorry, do it again. But there's a problem. So there's a telescope in South America, in Chile, on the Atacama Plateau. So the Atacama Plateau is this highly elevated plateau about 5 kilometers up, where there's a bunch of radio dishes, and they're put there because they work at a radio frequency that water absorbs. And so there's very little water in the atmosphere there. And so you can get these beautiful pictures of the thermal emission in the universe and the thermal emission from disks of material around stars. So the dust in the solar system emits because it is heated by the sun, and it emits at infrared wavelengths. And so you build these infrared telescopes on top of Atacama, and you can make these really beautiful images of young stars that have dust going around them. That dust is caused by material slamming into each other, and you get dust, and it warms up and you can see it. And the idea was, oh, we should look and we should see stars that are 10 billion years or 10 million years old, 100 million years old, 500 million years old, who have material still slamming into each other, because we saw the lunar surface has these old craters that are 600 million years younger than the Earth. So we should see stars that are 600 million years old, and there's still stuff smashing together and producing dust. And we don't. We have looked at hundreds and hundreds and hundreds of stars, and they do not exhibit this property. They have around 10 million years or maybe up to 20, you can get this happening, but not 200 million years. After 200 million years, it's all gone. The process of planet formation is done around these stars that we can see. And so it's a real or it's completely different. It's way more consistent with that first picture of things happening fast. Okay, so there's a real mystery. Do things happen slow or do things happen fast? And what's going on? And we don't know. And we can make both of them work because we can just tune our models and put in different physics. And what we're trying to figure out is which of the physics is right. And we're trying to constrain that by these observations. So very curious. Okay, so I do science that is very much driven by these kinds of plots. So here's a plot of something this is the size of objects, and this is how many there are. So I spent all my days looking at plots of the number of objects versus how many there are. And what we can see is that there are very few big objects, down around 1 in this particular plot, and there's thousands of small objects. And you can see many curves there. These are all models that were done by a team. Jake Simon is the lead. I can't remember where Jake is. And you can kind of see they all look basically the same. They have very similar shapes. They have a characteristic shape to them. And these are plots of what the size distribution of things between 10 and 500 kilometers should look like if that fast process is right. Okay. And it's only recently that we have the computing capacity to really probe. And the reason there's lots of different shapes is they've tuned various parameters that are expressed here. And you can see, you know what, it's not too important what the parameters are. This is kind of the general shape you get out. Okay, so that's for these small 10 to 500 kilometer size things.
Quick question.
Oh yeah, please. So these are log plots, and they essentially are log probability plots. So this is the logarithm of the size, and this is the logarithm of the number. So,
looking at probability that area under a bell curve.
oh right, yeah. So if I did it that way, basically that would be the peak of that probability distribution would be here, and then there'd be extraordinarily low probabilities down here. Yeah, but they don't. In fact, it's exactly what you're saying. In the next diagram I'll show you is the exact same plot, only we thought they would go to straight lines, and if you use that slow process, they go to straight lines. So, and this is a very complicated plot by Hilke Schlichting. And what Hilke did was build planets not from that quick process, but by 1 kilometer size things, and they collided together and grew and grew and grew and got bigger and bigger and bigger. And this is the line where at 1 billion years after the start. This is 2 billion years after the start. This is 3 billion years after the start. And that's 4 billion years after the start of her simulations. And this is representative of the work that's being done here. Others have done similar things and come to the same kind of outcomes. And you can see that it's not exactly the same. There's a lot more waviness to this structure. And there's straight line components to it. And there's a lot of interesting physics that goes into why it's like this. And then there are these lines here that are observational lines about constraints we have from other thoughts that people have, but I don't want to get into them too much. And you can see that though, if you look at this line down here, the radiuses that they're talking about go from hundreds of meters to 100 kilometers. If I go back, this goes from tens of kilometers to hundreds of kilometers. It's a completely different range of sizes. Okay. So what we thought we would do, this is Lynn Jones. She was a postdoc working at the University of Victoria for a number of years. She's now the Solar System Science Coordinator for the Rubin Observatory that's being built on in Chile. it's going to do this fantastic survey of the entire sky every night for 10 years. What Lyndon did was she led a project with us called the Canada, France, Hawaii Telescope Ecliptic Plane Survey. And we use the Canada, France telescope. This is Canada's premier optical telescope located on top of a volcano in Mauna Kea in Hawaii. It's a 3.6 meter telescope, and you can see a lot with it. I like this little animation that kind of shows you the stars going by here and the telescope rotating a bit here, so we can see inside of it what's going on. Because I think it's going to spin around really quickly. We'll catch just the end here. Yeah. So CFHT is fantastic, and one of the things that makes it really amazing for us is it's run in what they call Q mode, where the astronomers we sit at our desks and we write in forms into a computer system, and the computer does the observing for us. So when I was a grad student in the 90s, to use this telescope, you had to fly there, and you had to hope that when you were there, it wasn't cloudy, and then you could do your science. And then you went home, and you could only do things that would take you 3 or 4 days. To do this kind of survey that we did, we programmed that telescope to take observations pretty much every night for 4 years, but just for an hour or two. And then we shared those nights with other astronomers using this computerized Q system. Okay, so that's the way Lynn and I did that project. And in addition to that project, we have another project that we then followed on, which we called the Outer Solar System Origins Survey. And what we're doing is we're surveying the outer solar system. We're trying to find material in the distant solar system in the area called the Kuiper Belt. And the reason we're looking there is because we think that material never experienced any kind of real evolution, any changes post-formation of the planets. And we think it's a kind of a place we can go and measure what it was like right after the planets formed. And we could get an answer to this question of what is the shape of this number of objects per unit size. What I'm showing here is a little bit of another very astronomer kind of plot. This is a view from looking down on the solar system. And then you have the right ascension labeled around the clock here. So this is at 6 hours right ascension, 4 hours, 2 hours, 0 hours. So if you look outside tonight, at midnight, if you went out directly overhead at midnight tonight, you would be looking at around 10 hours of right ascension, looking off at this direction of the sky. And then the yellow areas are areas where we did one survey, and the blue areas where we did another survey. And the gray thing is a part of the sky that we can never look at because that's where the galactic plane is. It's horrible to look there. There's so many stars. And then the dots are all the objects we found and how far from the sun they were. So here's the sun. And so there's dots going out to about 50 times the Earth-Sun distance. So those are the dots and these are the different projects and the people who were the lead authors on those projects. And Michelle Bannister was the one who finished up this stuff at the end. And here we have a plot, again, in kind of sciencey plot here of how far away from the Earth, the sun something is, versus how tilted its orbit is. And then this is, instead of saying how far from the sun it is, this is how far from the sun is it on average. But I would say just draw your attention to this, that right, as you get out to around 50 astronomical units, basically our knowledge of the solar system ends. We really don't see, we've done these projects for 2 decades now, and it's very hard to find things in this distant region of the solar system. But we do see this little zone here at around 40 to 50 AU, which is really compact. And we think that's telling us something about how planets formed. And this is Michelle Bannister. She's now a faculty member. She was a postdoc at the University of Victoria for a while, and now she's a faculty member at Christchurch in New Zealand, which is where she's from. Okay, so back to one of those crazy, those plots I was showing you. So this is now the size of the objects. Only I am an observer, so I put the biggest things on this side and the smallest things over here. And this is the number of objects. And that looks a heck of a lot to me like those curved ones that we started off with, the slow process ones. It's lovely and curved. And we wrote a paper that said, this looks like the curved ones. Okay, and people were like, yeah, this is probably right. Scientists are always careful. And then there's some different functions, and there's different ways of presenting data, but it really was important. And so we think, based on this, that slow process looks like it kind of wins. But it's not so quick. Okay. So I've now overlaid some plots to kind of try to show what happened. So remember the plot from the very first. Actually, I'll just go back to it quickly. Right. This is from 100 kilometers to 100 meters. And this is from 10 kilometers to 500 kilometers. And our observations are from 500 kilometers to 10 kilometers. And so if I squeeze that down, I can put the curvy lines on top of it and they look like they're right. But what happens at the other end? Well, I can actually take this plot and fit it right on to just this tail end. And then these lines go off in their weird directions again. And so she would argue that actually you haven't shown me that this is the fast process is right. What you're showing me is the fast process is consistent with the big things, but the fast process predicts the big that would go all the way like that. And until we get to these smaller ones, we're not going to know. Okay. So what can we do? From the Earth, we're pretty much stuck. We really can't see smaller objects from the Earth. They're too faint to see. So we send a spacecraft. And the idea is to send a spacecraft to an object out there, and not to measure the individual objects themselves, which would be kind of really cool, but to find one and count how many craters it has on it and how many things have hit it. And the bigger the crater is, the bigger the thing that hit it. And so we can get not just a distribution of the number of things, but the number of things that hit this thing. And that will tell us the kind of the ensemble distribution of material. So if we see a bunch of really tiny craters, then we know there were lots of small objects. And if we see a bunch of really big craters, we know there were a bunch of big objects. We should just be able to do that. And the camera that we do that with is this thing called LORRI, which is a 20-centimeter telescope. Okay, and so it costs $1 billion to send a 20-centimeter telescope to the Kuiper Belt to make this kind of measurement. That's the scale of the enormity of this mission. So this is going to fly out. This spacecraft flew from the Earth all the way to Pluto, and then is now a little bit past Pluto.
Wow.
And it's only looking at those objects in that distant region, and that's all it's going to look at. At the very edge of our solar system. Yeah, at that absolute edge, and soon beyond it.
Is there significance to the names for the various systems?
Well,
I'm thinking
Yeah.
Camden.
So yes, exactly. So there's Ralph and Alice,
Okay,
who were the honeymooners,
yes.
right? And Pepsi failed attempt at corporate sponsorship.
Right.
Rex is sort of a homage to dinosaurs. Okay.
Okay.
And then I don't actually know what swap, why they called it swap. And-
They're counting students or the dust?
Oh, this is a dust counter that was built by students.
Okay.
So this undergraduate class at the University of Boulder built this instrument. It is the cheapest space instrument that ever succeeded. Okay, I'm going to show you some data from the student dust counter later. I mean, it was on a rocket. You just had to stick it on the spacecraft, but they basically built that instrument for a few tens of thousands of dollars, and it's unheard of in space exploration. It wasn't supposed to work. It was supposed to just be an outreach activity.
John,
Sorry, I have a question there.
yeah, this is from Zoom here. Yeah, could you just clarify, you had two models of planet formation. One was kind of, inside a cloud, and then all these things kind of hit each other. And then the other one was more like, galactic swirls that eventually kind of, okay. Which one is the fast one and which one is the slow?
Thank you. Yes. Okay. The galactic swirls happens really quickly. It takes about 4 orbits of those swirls going around the central body for the planets to form. And the one where they are all kind of hitting each other and forming in this giant disk, that takes 100 million years. The swirls take 100,000 years.
Okay.
So when I say one of them is quick and one of them is slow, I mean like one of them is really quick and one of them is really slow. And in 1990, 95% of planetary scientists you asked would tell you the fast way was ridiculous. There's no way planets only form, that it only takes 100,000 years for Jupiter to form. That makes no sense. If you ask them today, you're probably closer to 50-50 because we're learning so much that about how planets form.
Will you be able to show
Oh.
those 2 videos at some point again?
I-
Show the beginning?
Sure, I will go back to it because it turns out they're like critically important. Yeah. So this is Pluto. So New Horizons, its primary target was Pluto. Here's what Pluto looks like. Fascinating world, all kinds of things you can learn. One of the most frustrating things for my science field is that Pluto is active. So this surface here is a gigantic nitrogen glacier that is reforming and changing. There's methane ice flowing around. There's deposition of carbonaceous material. There's activity. It's an active planet and not useful for the process of counting craters because it's changing. And so you can count the craters, but those are just the things that hit it recently. Just like that's why you can't do this on Earth, right? You can't walk around on Earth and count all the craters that hit the Earth over 4 billion years because it wipes them out over a few 100 million years. So, but Charon next door looks like it's less active, way less active. And parts of Charon, like here, appear to be pretty good places to do this crater counting. So we did that, and we found that there were not very many small craters. You can kind of look here yourself and just see, there don't seem to be very many small craters there. There's some big ones, and then they just disappear.
No, it's Pluto's moon. Right?
That's Pluto's moon, Charon.
Captured
Yes.
something, yeah.
Somehow captured the same way perhaps that our moon was captured. Yeah. So what's going on are there too few craters? Now,
Excuse me, what do you
Yeah.
mean by the small crater? I see all kinds of little tiny craters. What do you mean by?
okay, yeah. So let's look, for instance, in this area here. I don't know if you can see where I'm pointing on the screen, but in the lower left-hand side, you can see some really nice smooth areas where there's not many small impacts. And by small, I mean just barely resolvable. So there's lots of craters, but when you count them, you discover there's really not that many small ones. However, researchers were not convinced by this, who were reviewers or people in the community looking at it, like, it looks to me like Charon's just active and it's wiped out the small craters. They've eroded away. And so you don't see them because of erosion processes, not because they weren't there. And we still don't know the answer to this question. Okay. What do we do? Well, that is the last image the spacecraft took of Pluto as it went past. New Horizons was traveling at about 14 kilometers per second as it passed Pluto. It was a very brief mission for the actual encounter. And we can't go back and redo the imaging or anything, right? So that's not going to work. It's a lovely picture. I mean, you can see the atmosphere of Pluto causing the sun's light to illuminate there. It's a beautiful picture. Yeah. It's mostly nitrogen. It's a very, very thin nitrogen atmosphere with a tiny little bit of methane mixed in. Yeah. Okay, so we got a spacecraft. We can turn it. It's going at 13 kilometers a second. We can turn it at 14 kilometers a second. And we can turn it at 150 meters per second. So that is, imagine you're going in your car. You can make a tiny little adjustment to the direction you're going. You can't change your velocity a lot. You can't go from going this way to going that way. You can go this way and then you can turn slightly. It's about a half a degree turn you can make. You're not going to change direction very much. So we would need to fire the rockets basically right after the Pluto encounter if we fired the rockets at 32 AU, then there's only about a 0.1 degrees on this, from Earth, there's only like this 1/10 of a degree that we need to search to find something for the spacecraft to get to. Now, the team had been doing this search for a decade before the encounter, because they knew this was coming and knew something they wanted to do. And in 2012, or thereabouts, we were doing those projects I talked about where we did this survey of the Kuiper Belt that Lynn Jones was leading. And we came up with a model of what the distribution of orbits looks like out there. And so the NASA team called us and said, we're not having success finding this object. What is there somewhere else? Is there anything you can tell us? Is there some insight you can provide? Because you guys have been doing that modeling. And so we did some checks and we realized that they were looking in the wrong place. So there's just this tiny piece of sky where you need to look. 1/10 of a degree, right? If you hold your thumb out at your arm's length, that's about 1/2 a degree or somewhere abouts. So 0.1 degrees is a tiny little sliver of sky. So you're gonna point your telescope, you gotta know exactly where you're looking. It's not like, oh, I can kind of see over there. So we did a lot of calculations for them. We found the part of the sky where they should be looking. And then we used the Hubble Space Telescope to look there. And we found a target for the spacecraft to go to. So that's what this little thing is. So here's the Kuiper Belt way out there. There's the sun in the middle. Pluto's the yellow line. And the spacecraft's following that trajectory. We're basically looking along here for where something should be. And the reason that you can't just say, oh, I'm just going to look down where the trajectory of the spacecraft is, you want it to be the thing, you want the object in 5 years from now, you want the object to be at the same location of the spacecraft. So you have to kind of look downstream. And the objects all have to, it's like, yeah. The duck's gonna be. You don't want to shoot where the duck is. It's not there anymore by the time, yeah. So we've got the same kind of problem, but here we don't know that all the ducks have different orbits. And so they're all moving in different ways. And what we came up with was a correct model of what that distributions of orbits was like, so we could figure out where the most likely place to find an object was going to be.
What kind of objects are you talking about?
So these are Kuiper Belt objects. So they're basically like asteroids, a few hundred to tens of kilometers in size, and they're orbiting around the sun out beyond Pluto.
So if you just drove straight into the Kuiper Belt, you might just see nothing.
That's right.
You go right through.
You go right through and see nothing.
Oh.
In fact, if you weren't from the ground telling the spacecraft where to look, it would never find anything. It could search the whole sky constantly. It would never find anything. There are not that many out there. Yeah. So you need to look this way so that these things can move here and be seen by the spacecraft. Okay. Oh yeah, and that's the field we need to look in, and it's a messy field. Okay. Now, we just started doing this search, and as I said, they weren't successful at finding anything, but they did find finding anything for the spacecraft to encounter. But a lot of things were found. So this is a schematic of the things that were found. And so there's the spacecraft, this little triangle flying along through space. Here we are at the beginning, we're at Uranus, then we're at Neptune, then we're 40 astronomical units, 50 astronomical units, 60, and the spacecraft's just chicking along. And each of these dots is an object in the distant solar system that was discovered during this search.
Wow.
Okay, they're all too far away for the spacecraft to do anything with. That doesn't make them uninteresting. And so as we flew past, we turned the spacecraft and looked and take measurements of them. And these are measurements that are impossible to get from the ground because you're looking, right? If the light's directly overhead, you have this one way of seeing things. But if the light is when the moon is at first quarter, right? You can see these features of the shadows cause these features on the surface of the moon. Same thing with these objects. You can see these kinds of structural features because of this large angle illumination. Yeah, I'm going to play that one more time. Exactly. So there it is. There's the spacecraft. We were looking along here to find something for it to go to. That's why the white dots exist and not stuff way down here. And then this is the field of view, basically as the spacecraft's flying along. That's what it sees.
Wow.
Yeah. Okay.
And then at the end, that kind of shows that if you don't aim it right, you could just be seeing that.
Yeah.
Not seeing all the other stuff.
That's right. You just see nothing. Yeah.
Wow.
Yeah. Yeah. So that was a great search. We found lots of things for the spacecraft. We also found a target for an encounter. Oops. And I'll just point out that, so this is Anne Verberscher. She's the project scientist for New Horizons. And her favorite thing is to observe these objects at these large angles and measure the structures of their surfaces based on this technique. And she has now published, I think, 5 or 7 papers with about 30 objects that we measured in this way. So we're really starting to understand the structure of the surfaces of Kuiper Belt objects, which are cool in its own right. Well, we did find something which we called Ultima when we first found it. Okay, so some of my slides say Ultima because these are slides that were made up right at the time of the mission happening. We now have given the name Arrokoth to this object. The spacecraft's flying towards it. We've adjusted the course of the spacecraft. We didn't even have to use the whole 130 meters per second. We only had to use about 55 meters per second of change because of how nicely it was aligned for us. So this is 37 hours out. This is the first resolved image of the object that we're going to fly up to in 37 hours. So this is an engineer, space mission engineers, just, they hated this project, okay? You're telling them, I'm going to give you the first image anyone has ever had of this thing that isn't just a dot. And we want you to fly right up to it and take a picture for us. You're going to get your first image 37 hours in advance. Oh, and it takes 13 hours to get a message back and forth, or a message there, another 13 hours to get it back. So you're basically going to get this image, and all you can do is say, ah. So they had an upload ready to go to just turn, if this wasn't right in the center of the field, to just tweak slightly the path. And actually it wasn't so much to tweak the path as it was to abort. So we were going to fly, well, we did fly 3,000 kilometers from the object. And if that thing hadn't been in the center, we would have flown 10,000 kilometers from the object. And if you're farther away, your small camera has a bigger field of view. And so you don't have to know where the thing is as carefully. But we got this image of these little pixels, and they told us that the object was in the center of the field of view. We did not need to change our plans. And I show you this because this is the data you get from the spacecraft. And this is the data that the press gets from the science team. Okay, so we didn't do that too often, but this was one of the most shocking ones of, wow, you guys really sharpened that image up nicely.
Photoshop.
Yeah, that's been photoshopped pretty heavily. So yeah, so there we go. We're on way, 37 hours out, looks good. And then about 24 hours out, we get this picture, which is now almost impossible to see in this room, and that's kind of appropriate for how much this told us. There's a little blob here. It's a peanut-shaped blob. Okay, we already knew the object was peanut-shaped because we've been doing occultation studies of it, but we didn't know if it was 2 objects or 1 object. And this was another problem with the whole space planning and the flight plan. If you're flying up to 1 object, you do one thing. If you're flying up to 2 objects, well, that's a different problem. And we couldn't tell them if it was 1 object or 2 objects. We didn't know. Okay, one day prior to closest approach, we get that. It's starting to look like it's probably 1 object. And that is a unphotoshopped fuzzy blob of the first approach image, the one-day approach image. The final image we got before it's like 24 hours. It's too late to do anything about it. Okay, and that was the very first image we got down the ground on a computer screen. Stuart here. So everyone was sitting at their desks we were all monitoring the downlinks, and there was a hard drive that the space comms would write the file to, and people were literally like hitting reload, trying to load that file as it was being written to disk. And eventually the team said, stop. We're gonna, we're gonna crash we're gonna bugger the file up. something bad is going to happen. We're just going to get one person to do it. And Stuart was the guy here, was nominated to be the person who would load the image. And we just gathered around to have that first. And this was essentially, there was a photographer there, taking pictures of stuff constantly. This was the exact instant when we finally saw what the heck this thing looked like. And
Wow.
I mean, they're really, these are not, this is not a stage photograph. I don't want to look like you're really amazed. No, this was just that exact instant when it came up.
I
So,
always wondered about that.
yeah. No, yeah, there's a really, there's a guy who writes books who was there and he was taking these pictures. It was very good. So that's what it looked like in the control room. And I'll just show you that. So, okay, so it's taking this long delay time, right? So you have to decide what it is you're going to downlink, because it takes 13 hours to get the signal back, and there's a limited amount of data you can send. So we were only sending the minimum amount of information just to figure out what's going on. Okay, so that was picked out for that reason. And here's the entire sequence of data that we originally downlinked. There it goes. That is the entire encounter. With okay, and that's the data block we downlinked for that. And you had to know, that's why we're all hitting reload, because each frame was coming down individually. Nothing. Oh my gosh, it was exciting. Okay, so there it is again. And that's the object stationary, right? That's the spacecraft flying by. And it's staring in one direction. The engineers were like, well, that's where we're going to point. And tick, 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 tick. And we were like, okay, they started taking images about 6 minutes before we predicted we would fly past it. And they continued taking pictures for about 6 minutes afterwards. When we downloaded the 10 seconds, what we thought the thing was going to be. Because we're scientists and we know where that thing's going to be. The other thing that's really impressive about this image, I mean, we were damn lucky, okay? There's no doubt about it. I'm just going to pause it here. Oops.
It looks like two.
Yeah. Gosh, I'll try one more time. How can I pause this in the right spot? Here we go. There we go. So that's what it looks like. This is the full frame of the camera on our little telescope.
Wow.
That's the last row of pixels on the camera. And that is the sliver of the bottom of the object coming through. We got a few tens of pixels at the top. It didn't quite see it properly. It's like that worked.
Amazing.
It could not. This could not have happened without an enormous amount. So
How large is it?
so this from here across is about 37 kilometers. 40 kilometers, so that's like 25 miles.
Okay. I'm gonna ask a dumb question. What am I looking at?
Right. Okay. It's not a dumb question. We didn't know what we were looking at either, really. Okay. So this is like a rocky body, maybe made from ice, that's about 20-ish miles, 40 kilometers in size. Okay.
Well, it's not a meteorite.
It's not a meteorite. It's about 40 kilometers in size, and it's in space, orbiting around the sun, farther away than Pluto. This object is about 43 times farther away from the sun than the Earth. Okay, and so we found it. We figured out exactly where it was. We took a spacecraft that was already flying in that direction, tweaked it slightly so it would fly 3,000 kilometers off the surface, because that's how close we thought we could get before the object would fill the field of view. The reason we knew how big the object was because for about a year before we got there, we were deploying little telescopes that were about 12 inches, in diameter, these 12-inch telescopes, to different places on the Earth where we had predicted that this object would cross in front of a star. We would time how long that crossing took. It's called an occultation. So the star would be blocked by the object going across, just like an eclipse. Only this is now a distant star being blocked by this object. And from that information, you can figure out, you can say, oh, I had 25 telescopes on the surface of the Earth spread over 100 kilometers. And the 10 in the middle that were spread over 30 kilometers, they saw something. And the other ones didn't. So this thing's only that big because its shadow on the Earth, even though it's tens of billions of kilometers away, its shadow on the Earth is just going to be the same as, you know, whatever its size is. So 20 kilometers. So we measured its shadow using these small telescopes deployed on the Earth's surface.
What makes this thing so interesting that you spend all this time?
Right. Yeah.
Good, what?
So this, I'm going to go to the next. Well, I'm going to go a couple slides and I'll show you
We're with you, we're with you.
Okay. First, I want to say the first thing we said was that is really weird. It's like these two blobs stuck together. We were calling it a snowman. It kind of looked like a snowman. It was January 1st. We had that kind of thing on our mind. But maybe we shouldn't. Okay, this is almost embarrassing. So these are 3 other objects we already knew about. It actually looks exactly the same as the other ones. So it looks like Comet Halley, it looks like Comet Borrelli, and it looks like Comet CG. The difference is that these comets, this thing is about 40 kilometers across. These things are 1 kilometer across. But they have the same 2 things stuck together.
Yeah.
Yeah. This, people were always arguing about whether or not that's how they formed or this was some evolutionary process. We go out to this thing, it's like, no, that's how it formed. There's just no way, you can't get things like that through some evaporative thing. That is just formation. And in particular, you can see it's a little bit brighter here. There's an impact ring where the 2 pieces touched and formed into a single body.
Or you might hypothesize that if you took your discovery and threw it close to the sun, thousands and tens of thousands of times, it would eventually
Right.
warm down to about 10 times.
So that is one way to think about it. That might be right. But what I think happens is that you form things at this scale and this scale the same way. This object is not a bunch of these things that stuck together. This thing, which is 40 kilometers across, formed the same way as this thing that's 1 kilometer across.
Then they're gonna get as big as that eventually?
I don't think they are going to change much in their sizes, but they seem to have been born in the same way. It's like you discovered that children could be born and they could be a foot tall or they could be 10 feet tall, and that was the exact same process. And they didn't grow.
Do you know what it's made out of?
So the camera on board was sensitive to light that would be absorbed by methane ice. And there's a tiny hint that we see some methane ice on the surface. Really super tiny hint.
But there is no spectrometer on that.
There was a spectrometer, but it was the signal from this thing was so weak, we just have noise. Yeah.
Were they found like in all different places or were they found
These things are all coming from that Kuiper Belt region.
all in the same?
Yeah. These are comets today, but they started out there. Yeah. Okay, so that's one kind of thing is, okay, what's going on there? Oh yeah, this is just a sequence. I'll run that again. This is all the data. So this is 100% of all the data because we took some images from farther out, right? And on approach, and we had some stuff. I just showed you the best single shot, but let's just run through 100% of the data taken for the mission. Okay, and now you can see the rotation, right? So it's called derotated because they've taken out the spacecraft's motion. And so you should just see motion of the object itself. And they try to put it all at the same scale. And I don't know if you can make it out without me telling you, because once I tell you, you can see it.
Face.
The face. Okay, but look at the shape of the large lobe as it rotates around. It's square, yeah, but you're cheating. I've shown you this picture before.
SpongeBob SquarePants?
It's-
I don't know.
It's flattened.
Oh, it's, yeah.
Yeah. It's not a,
Potato.
it's not a round thing. Okay, and we think when stuff accumulates together to form planets, they're round, right? This did not accumulate into some round shape. This accumulated into some other kind of shape and has not changed shape under the pressure of gravity into a round sphere. Gravity will make, if you give it enough mass, it turns into a round thing. That's what gravity does. And so when you look at a round thing, you're looking at a highly processed, evolved object. This is not a round, highly processed, evolved object. This is whatever it formed. It hasn't changed. So we are looking at a pristine remnant of the processes of planet formation.
You would see with it, I would think that it spoke off of something on. I mean, that would be the assumption of a
Yeah.
novice, you know, because it's not round.
Yeah.
Expect it to be round.
Right. Yeah.
Well, it's just like a-
It looks like a big thing that smashed and this is a chunk and yeah.
How large,
But that's not the case.
That's not the case.
No,
how large would something have to be for gravity to be able to round it out?
Around 200 kilometers.
Yeah, and
This
that's way
is
small.
way smaller. So it's not round and so things don't form round. They form in this other kind of shape, which is a signature of the process. Is
So
it
this is probably considered young.
very young? Yeah. Yeah, this is like looking at a brand new object. Except that it's 4 billion years old and just hasn't changed. Yeah, it never grew up. Okay, so this is Kelsey, this is Sarah Greenstreet. And Sarah and I worked on this problem where we thought, okay, then this is before we saw Arrokoth, and I like to stress that to everybody, okay? Before we got there, we said we should actually make a prediction because we're kind of scientists and scientists are supposed to predict things. Okay, and so this is a bit of a plot, but anyway. So this is how big the craters will be. And this is how many craters there will be in some horrible scale that I don't want to get into. Okay, there are two models. Either we get more and more craters as you get to smaller, or we get fewer craters as we get to smaller. Those are pretty, stark contrasts.
wishy-washy.
Nothing wishy-washy here. This is that model from slow processes. And this is the model from fast processes. Okay. And so at the very start, I showed you the plot from Hilke-Schlichting where it went up and there was more and more small things. And that is not what happens in the fast process. That only happens in the slow process. So if the slow thing works, we should get a distribution of sizes of craters that goes up. And if it's the other process, this fast process, it should go down. So we made this prediction, we wrote this paper. Oh, I think I actually have some. Yeah, okay. And what's really driving this is that this is what you see in the asteroid belt. And so people have looked at the asteroid belt and said, that's the signature of how planets form. And another community has been arguing that asteroid belt is heavily processed and it doesn't represent actual planetesimal formation. Okay. So Kelsey Singer, another scientist on a mission, looked at the image and she counted all the things that she thought might be craters and measured how big they were and how many pixels across they were. So you can kind of see the ones up here, 18, 6, 7, and 8, or 8, 6, 7, 8, and 18, and 44. And 1, I mean, that's a nice one, eh? 1 and 2 and 3, those are 4. These ones are great. Maybe there's a crater there. Maybe there's a little blob. I mean, this is the best data that's ever been acquired on this problem. We're trying to just tease out the most we can. So she's counted them all up and then she grouped them into ones she thought were really good, things that were, maybe okay. Okay. And she measured the sizes of all of them. And now we can, and Kelsey wasn't on the prediction paper. That way we would have independent, like there wouldn't be a conflict of interest, okay? So the first thing is there's a big crater, and go back here. Okay, this is the crater. It's very big. It's called Maryland by the team. I don't think the international naming committees have accepted that as a name. Maryland is where we were when we saw that image, so that's
Which
Maryland.
number?
Anyway,
Which number is it? Which
Uh,
number?
Number 23.
Okay.
Okay. And I don't know why it's 23 and not 1. So, okay. So there's Maryland. One big crater. And I think you can see from how the plot's made where the other ones go. So if we look at just the absolute best ones, there are fewer craters as you get smaller. Okay. If you look at the ones that are maybe okay, they follow the same line. If you look at them, oh, that really could be. Okay. And that's with, you say, okay, that's everything that I could look at, any little smudge that I thought might be a crater. There is no way to get there to be more craters as you get smaller. There are fewer craters as you get smaller. And I will draw on our prediction. Yeah, there it is. So that is how it looks when you put it on top of the prediction plot. It is completely consistent with this scenario. Planets form quickly. That is what we learned from New Horizons. And it's a transformative piece of information in understanding the processes by which the Earth came into being, by which Jupiter came into being. And we know it because we've made these measurements. And we predicted what it would look like. And then we went and measured it, and we saw what we saw. So this is not right. It doesn't get, there aren't more and more things as you go smaller. The number of things stops growing. Eventually, you just get a flat line here. There's not more and more things as you go smaller and smaller. The process of building the initial things, initial building blocks of planets is driven by hydrodynamics and fluid dynamics, which are the hardest problems in physics that we didn't have the computational capacity to approach properly until the last couple of decades. And really, we're just now getting to that. Yeah.
I would agree that the smaller things were just not tough enough to make it.
So there are referees who say, who come back to us and said, if I go back to the surface of Arrokoth, and they're like, okay, maybe the surface is kind of spongy. And so the small things hit and they didn't make a crater. They just kind of went bloop on the surface. Okay. And that's fine. You could argue that there's some kind of crater size, a relationship between the impactor size and the crater size that scales differently for these kinds of objects than for impactors in laboratory experiments on Earth. And that is actually completely not a crazy idea because this thing is made up of methane ice and is not gravitationally bound. It's not, it didn't get crushed into a circle. So we don't really understand its physical structure very well. So maybe the impact crater sizes of craters don't scale the same way we think they should. So we did an entire analysis of trying to find a relationship that would allow this to be a scaling problem where the small craters just disappeared because of the way the surface behaves. And we could not find a scaling relationship that we thought was plausible. It had to be basically that a 1 kilometer or a 100 meter thing hits this and just goes splat onto the surface. And I don't know why it would, because when you look at them in labs, when you do the scales, that's not what happens. So, but it's possible. So we may not have cracked this nut, which, it's science. Someone will figure out something.
Question.
Yeah.
Do you have an estimate of its density?
Ah, yes. So because there's the two lobes stuck together and it hasn't crushed, we know generally the mass of the system and we know its size, and so we can get it there. And so it's around 300 kilograms per meter cubed, or 0.3 grams per centimeter cubed. So it's about a third the density of water. And that's actually the thing that made people say, I think the craters don't scale the way you think they do, because we've never done impact experiments into something that fluffy. And maybe the fluffiness is what you're seeing. And that is a That is a problem that we cannot address. We just don't, no one has figured out how to work that
The
out.
fluffy snowman.
The two fluffy snowmen hit each other and they didn't make a hole. Yeah. So. Okay, I'm gonna wrap up quickly here. The spacecraft's still healthy, working great. It's flying at 12 kilometers per second out of the solar system. Every year it goes 3 astronomical units. We are desperately searching for something else for the spacecraft to encounter. There is a 1% chance that we will find something.
What?
1%, 1-ish. Okay, we don't want to say it's less than 1% because it gets too depressing.
Your funding goes.
And our funding would go away. But you can see here, the spacecraft is about right here. Okay, this is the stuff we already know about from these early surveys of what's going on. Okay,
Okay,
there's not much stuff out there.
Where is here? Where is here?
Pardon me, sorry, the person online?
Yeah, where is here? What
Oh,
number?
here. Oh, that's around 60 AU is where the spacecraft is today.
Okay, thank you.
Yeah,
So why is it advanced around 35, 40?
that's, yeah, so that's where the Kuiper Belt formed. And we don't know why it formed there, but that's where it is. That's it.
Going that direction?
And the spacecraft's basically flying along here.
Okay, so you've gone through that.
We've gone through all that. Yeah, and that's where that picture of those things
Yeah,
stripping
that's
by, okay? Yeah,
Can't pull a U-turn.
yeah. So this is where in the sky we need to look if we're gonna find something for the spacecraft to go to. It's that little black box. There's a star called Pi Sagittarius that's right in the field where we need to look. We're trying to look with an 8-meter telescope at a first magnitude star. It's causing all kinds of trouble, but we're working on it. Here's Jupiter and Saturn. This was a night I was observing in June of 2020. And it was a beautiful night. So it's a picture and then put some labels on things. Anyway, that's where we're looking to try to find something. That we're looking with the Subaru telescope. This is the camera we're using. It's called the Hypersuprime Cam. It's enormous. It's mounted on that telescope. That's the optics pointing up at the sky, maybe.
What are you looking for though? How do you detect?
We're looking for, yeah, so what we do is we take an image and then we wait a little while and we take another image, and anything that's moved has changed where it is in the sky because the Earth has moved. And so we're looking for the parallax effect of the Earth's motion, causing the thing to appear to move relative to the distant stars. And that's 100% of how we're detecting them.
What kind of magnitudes are we talking about?
So with the Subaru telescope, we are able to just achieve what's an R magnitude of 27. And that is right at the hairy edge of what we can do. And that's what this giant mirror.
The scope itself or the probe itself, it's unable to do any detecting. You have to do all that and then point it at the right place.
That's right. The probe there's a 20 centimeter telescope on board New Horizons. It could never do this. It's amazing, right? You're on the Earth, billions of kilometers away, and still the 8-meter telescope beats the 20 centimeter telescope. Oh, yeah. Okay. And this project's being led by Fumi Yoshida interestingly, at the Commercial Agricultural University of Japan. It's kind of, that's where she works as an astronomer. It's a super complex problem analyzing this data set. We've developed new software that's running on GPU systems, and we use machine learning techniques to do the analysis. It's very complicated. We're just learning how to do this. And what we've done is, this is all the things we've discovered over the first 3 years of trying to do this. Since 2019, we started. It's actually on to 4 years now. We found all these things that are interior to 50 AU on this plot. So the number 50 here, that's 50 times Earth sun distance. We found a whole bunch of stuff there. We found some stuff out beyond 60, which was weird. And we haven't found many things in the middle. And we're starting to think maybe we're seeing a second patch of material that we never knew was there, because we're looking for fainter things than anybody has ever tried to look for before. Maybe. It's still very tenuous. There's actually a second piece of information when I come back to the student dust counter, which turns out to now be a critical piece of infrastructure on board the spacecraft. It's named after Venetia Burney, who was the girl who named Pluto when Pluto was first discovered. What we're seeing here is these black dots are how much dust is the spacecraft seeing as it travels through the solar system. So it's just flying along and bang, 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 hitting dust as it goes along. And we just count up how much dust it sees. This is the number of dust counts per meter squared of the detector per 10 to the negative 4 seconds. So there's a dust particle or 3 hits this detector every millisecond or 10 something millisecond.
And that's on the crowd.
That's on board the spacecraft. And it's just a little plate of basically aluminum foil. And when dust hits it, it changes its capacitance and you can tell dust has hit it. So it's pretty frequent, right? There's a lot of dust out there hitting this thing. And bang, 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 bang. The red line and the black line are our predictions of what the dust count should be prior to launching the spacecraft. And sure enough, we left the Earth's orbit. Yeah, it looks like, yeah, these are error bars, because counts are kind of hard. So yeah, it's following along nicely. And everything was just hunky-dory till we got past Arrokoth. And the dust count rates were supposed to go down.
And the wheels fell off.
And they didn't go down. They stayed up. And the dust is produced by objects in the distant Kuiper Belt, cosmic rays from the rest of the galaxy hitting them, and dust gets bumped off the object. So these are electrons and protons that have traveled through the universe, through the galaxy. They impact objects in the Kuiper Belt and they push off a little bit of dust, and that dust hits the spacecraft when we count it. And modeling is it should have gone down here, and it didn't go down. It's staying up here. And that could be explained if there was another ring of material that was producing this dust, and that we just haven't seen it yet. We can see the dust, we just can't see the things because they're too faint. So we're currently begging NASA for money. So we've been doing this with the Subaru telescope, and then when we find an object, we follow it with the Hubble Space Telescope. We use a GPU, we get to V of 26.5, 27, okay? It's fantastic. What we want to do is we want permission to use the large, the Rubin Observatory in Chile, which will start operations in January next year. And we want them to give us about 6 months of that telescope's time, which they're not going to do. But anyway, we're going to ask. And then if we find something, we might follow it with Subaru, but we probably will follow it up with the James Webb Space Telescope, which is just recently in space. And if we can have 100 views, and we can do this thing, we think we can get 8 times more sensitive. And our chance of finding a target goes from a 1% or so chance to something like 8% chance of success, which starts to sound interesting. And we want to do that to rehearse for the real show, where the Roman Space Telescope will be launched in 2027. It can do this search if they give us, how much do we need? We don't even say how many nights. I think we need 100 nights on that facility. And then we can follow things with James Webb. And we're going to need 100 GPUs, and we can get to about 30th magnitude with this concept. And we think there's it was a 50% chance, basically. 1 in 2 chance of finding something else for the spacecraft to go to. So we can make this measurement again and see if it's gives us the same result or something different. And so that's what we're trying to do now. So, and that's the end. Yeah.
How many years until the probe leaves the Kuiper Belt?
So we thought it was already out.
Given that there's not a second.
Yeah, if there's no second belt, it's already done. It's gone. It's outside the Kuiper Belt already. If there is this other bit of material, it won't get there till 2029 at its current flight rate.
Just in time for Roman.
Pardon me?
Just beyond.
Oh, just beyond when Roman is available. Yeah, this all kind of lines up. And this mission has been all about things lining up. So we're hopeful. And then we could successfully have a third object that the spacecraft would encounter.
What's the lifespan of the?
Yes. So the engineers are hard at work because they told us it was going to die in 2028.
Oh.
And we told them it needs to live to 2033. And so they're working on it. Right now, the best estimate, they've uploaded new software to turn off pieces of the spacecraft that aren't needed. And instruments that won't be used anymore have been deactivated. So we're saving power. And I think through these various power saving measurements, we can get to 2033. And the spacecraft's so far away, we actually need 3 years to retrieve all the data after an encounter.
So how far can you have enough light from the sun to be able to image the object?
Yeah, so the 20 centimeter telescope on board, if we pointed at a 40-kilometer sized object, we can detect that out to about 100 astronomical units. So that's not a problem. They won't be the best images we've ever taken, but we could still make measurements. So yeah. Yeah.
Did the Saturn system give us any information? Is that a bad analogy?
Right. So the Saturn system has all kinds of small moons around it, and we measure the distributions of sizes of those small moons. But we're pretty sure that those are the results of collisions around the Saturn system. And so the distribution of sizes has evolved from formation, and it's not giving us the information we need to pick out between these two models. And I'm just before we go back, I'm just going to go back to the very first movie here. This is probably not the best way to do it, but anyway, that's the talk in reverse. Oh, right, have to undo all the billions of years. So this is the fast model.
Yeah.
And that is a good representation of what's probably going on.
I was pulling for that one.
Okay, and this model came out when I was just finishing graduate school, and I tell you, nobody liked it. And you know, these planets, you can watch that, it just takes a couple of turns around, blam, you get planets.
How many
Yeah.
people like it now? I got a question.
Oh, a lot. Yeah, it's pretty popular. Yeah, there's still a few holdouts, but
Based on your,
based on this mission's outcomes,
Yeah.
people have pretty much given up on the other process. Yeah,
Wow.
yeah,
or the success then?
very successful.
And what did they find out? What makes the turn?
What makes it turn? Oh, so we think the stars form by gas falling into the center. And as it falls in, any slight asymmetry will cause it to spin. And so what you're seeing is the spin just from the gas infall process. It is not always counterclockwise unless you're an artist rendition. Yeah. Yeah. But if you're in Australia, I bet it goes clockwise.
Gravity that's creating the planets.
Yeah, so what in this model, it's gravitational instabilities in this stream of material is what's causing the things to come together and forming the planets.
So what happens with all the other little streams?
So this was an early rendition of this, and I show it because it's really important to know that someone was thinking about this long before we saw it was right. There are newer versions where there's more uniform formation happening. So this is numerically a very difficult problem to do. And in the computer programs, basically you get round offs and you get incorrect force calculations, and things happen that are not physical. So some of what you're seeing here is probably not physical, but it appears that the fact that knots do form is a real physical process. So, yeah. Yep.
I got a
Oh, yeah.
question.
Sorry.
Is the middle of the earth is iron, right? There's a big.
Right.
You would think that takes a long time for all the heavier elements to move to the middle. That wouldn't happen in that kind of.
Right. So what we're getting to here is the end of the process by which you can say a planetary object is there.
Yeah.
But now there's going to be a whole process of settling as all the material gravitationally collapses into forming a round thing. The settling of the iron to the Earth's core takes tens to hundreds of millions of years to happen. Yeah.
It's still happening.
It's still happening. Yeah. Right. And that's what that kind of geological timescale thinking is where people were when they were thinking about planetesimal formation and planet formation. And that's why models like this were the one that really was the favored accepted process. And this is probably what happens. And yeah, turns out it's probably not. Well, evidence today indicates it's not. One has to be careful because 20 years ago, evidence was this was the choice. Come back in 20 years for an update.
That's what science is all about.
That's what science is all about.
Because what if the next object has all sorts of small meteors? that just-
Yeah, wouldn't that just be a real kick in the head? Yeah,
Okay.
yeah.
Thank you very much for your time.
Thanks.